All right, class, we're continuing our notes on solubility, AP Chemistry, Unit 3.10. Now, these are some of the different types of forces between solute molecules or particles and between solvent particles, and then we're going to talk about the forces that can occur between solute and solvent particles. Okay, so if we have ion dipole forces, those are actually pretty strong forces. So that's if you have a polar molecule and an ion. Okay, hydrogen bonds, that's between a polar bond that is attracted to hydrogen in an OH, NH, or FH bond. Very high electronegativity for those three elements. It leads to an extremely polar bond, which is a really strong dipole-dipole attraction is what you end up getting. We call those hydrogen bonds. A lot of times we put quotes around bond. Okay, and then we have dipole-dipole forces if they're both polar molecules. Ion-induced dipole, that's if you have an ionic compound that is dissolving in a nonpolar compound. Not a very strong attraction. And then we have dipole-induced dipole, still not very strong. These are actually really, really weak attractions. Okay, these two are weak, and it's important to recognize that. Dispersion forces tend to be somewhat weak. These are LDF, so dispersion forces, that's LDF. But remember, if it's really big, it actually can be a very strong force. So it can be stronger than even a hydrogen bond. And don't forget, that depends on the total number of electrons. All right, and then we talk about bonding. So these were non-bonding intermolecular forces, but now we have bonding, which is intramolecular forces. We have intermolecular, intramolecular, which is bonding. So the ionic bond and the covalent bond. Ionic, again, is electrostatic attraction between cations and anions, and covalent bonds are sharing electrons between them. Okay, so for each of the following mixtures, we want to describe what types of IMFs are dominant in the attractions between the solute and the solvent. So we don't need to list all of the IMFs, we just want to list the most dominant. So a way of thinking about this, if there is a dipole, but there's no OH or FH or NH bonds, we would say that the most dominant is dipole-dipole. If all we have is LDF, that's the most dominant. If we have LDF, dipole-dipole, and hydrogen bonds, then the most dominant would be hydrogen bonds. So we're just going to list the one that's typically the most important to what we're talking about, the most dominant one. So we have turpentine dissolved in toluene. Well, both of these look like they are nonpolar. So we have we have LDF between the solute and the solvent. So that's the other key thing to remember. We're talking about between the solute and the solvent. So the two different substances, what kind of attractions do they have? This would just be LDF because they're both nonpolar. Both of them. Then we have bromoethane. This one looks like it's at least slightly polar. And then we have acetonitrile. This one also looks like it's polar. I don't see any hydrogen bonding. I don't think there's any way that we could have hydrogen bonding here because acetonitrile says CH3, so that means that we've got 3 hydrogens on the carbon. And then C, so we got a carbon, and then N, it's probably a triple bond to that. And we could count it up and justify it, but just really quickly, that's the basic structure. There's a pole, but there's no hydrogen bonding that can occur because there's no NH bond. So we have 2 polar molecules. The most dominant attraction that we're going to see is dipole-dipole. All right, then we have acetic acid dissolving in water, and we know that water is H2O. It looks like that, and it is polar. This is polar, and it looks like we are going to have an OH bond. If we've got an OH bond in this, and we have an OH bond in that, then we could have hydrogen bonding forming. That's going to be our most dominant intermolecular force, will be hydrogen bonds. Potassium nitrate dissolved in water. So potassium nitrate dissolving in water. So we have a polar molecule, and this is an ionic molecule, or an ionic compound. So what we're going to have is ion dipole attractions, because the ionic compound will break down into ions. Let's go to the next page. So when does the solution form? When does the solution form? It forms when the relative interactions and solution formation, so that's what this table is about, it is going to form when the solvent and solute interactions are greater than or equal to the solvent and solute interactions. Okay, so we have to look at how they compare. In both of those cases, it would form. The other case, it says it may or may not form, so it kind of depends on circumstances, but we can make some predictions about it. So if your solvent-solute interactions are instead weaker than the solvent-solvent and solute-solute interactions, there's a decent chance it's not going to dissolve. There won't be a solution formed. So the solution forms when the solute-solvent IMF strength, so keep this in mind, the solute-solvent IMF strength is similar to or greater than the solute-solute and solvent-solvent IMF strength. This is key. This is basically what we mean when we say like dissolves like. If they have similar IMF strengths, then they'll tend to dissolve. So we talk about like dissolves like being polar dissolves in polar, nonpolar dissolves in nonpolar, and that's true. This is kind of giving an explanation behind that and a little bit more specific rules, so to speak, and we can answer some questions that we wouldn't have been able to answer before. Let's look down here. Okay, there's a solubility demonstration involving hexane and water. There's one with iodine crystals, hexane, water, and iodine crystals. There's another demo that we could do with hexane, water, and potassium permanganate. So I'm going to pause it now, and I'm going to link those videos for you guys to go ahead and watch those.